Hello, everyone, and welcome to our webinar series. I'm so humbled to see there's a lot of people, even on the 15th of December, joining in, so that's super great. A lot of people eager to learn a little bit more about certain technologies. Today, our webinar is going to be part 2 of how to set up a simple but yet powerful capillary zone electrophoresis method. And I'm just going to jump into my slides right here. By the way, guys, don't hesitate to use the chat box if you have any questions or anything during the presentation, or even after I actually open the doors for people to send in the question. Don't hesitate, put them in there. What's cool about this is they're all registered, so if we don't have time to answer them live, we'll be able to answer you via email. And let's jump into the presentation today. So today we will cover the summary of what we've covered on the first webinar on how to set up a simple but yet powerful capillary zone electrophoresis method, because I want you guys to kind of create the full story so that you'll be able to understand where I'm going with this. The next step, we're going to add another part of setting up a capillary zone electrophoresis method. And it's a part that a lot of people tend to forget, but it is a very important part. And this is what we're going to be covering today in our presentation. And then I'm going to end up with a segment called, Do You Need More Information? i.e., if you can send an email out to us, we'll be able to give you more information, whereas it's any of the projects that you might need on any of the systems that we can supply as far as that goes. Or if you have like a basic question on capillary electrophoresis, a mercury analyzer, an FTIR or an NIR, or even a graphite atomic absorption spectrometer. So I'm forgetting a couple of them. And oh yeah, let's not forget if you have like a PCR question with our really cool Ariadne PCR instrument, which by the way has a seminar tomorrow, a webinar tomorrow. So be sure you join in that action. All right. So let's jump into today's webinar, and part of the summary of what we've covered last time was I mentioned at first that we had 6 types of electroseparation, and they're all listed here. And of course, we're going to zone in on the capillary zone electrophoresis, because that's basically the technique, I would say, that covers most of what you need to understand for capillary electrophoresis and how to operate. It gives you a sense of pretty much all the theory around capillary electrophoresis, and that's why I wanted to jump into that specific electroseparation technique. You'll notice that the 5 others are listed there, and there's a reason why I list them there, and I'll actually mention that in my next slides. So let's move on to the next one. All right. So as part of building a very simple but yet powerful capillary zone electrophoresis method, as you remember, I've actually listed all of these during part 1. We need a system that has to maintain stable capillary temperature, and we actually do that with a coolant pump, which contains water. And I had forgotten to mention that on part 1, but I won't forget today. There's a little bit of methanol in that water just to prevent any growth formation in the water, because as you know, if it's just water alone, there could be some little algae there that would grow, and we don't want that. And we recommend 4 to 6% methanol. We need a system that has to be adaptable to various capillary sizes. I mentioned that on part 1 also, whereas we typically are working with 50 micron and 75 micron internal diameter. The external diameter of the capillary for bare fused silica is roughly around 375 micron. We need to have a system that has a sensitive detection limit, that has a robust high voltage power supply, because that's where the heart of the separation occurs. and it needs to have a capability to hold multiple samples and buffers. We have inlet positions from 1 to 59, and then outlet positions from 36 to 59 on the Capel-205 system. And the reason why we have an inlet position from 1 to 59 is we actually have a capability of shuffling vials around. So that's why we mention inlet 1 to 59. That might look a little weird, but that's the main reason why, is because we can shuffle the vials around. Before last, we have one line that I had forgotten to mention on part 1, which is this system doesn't use a lot of reagents. So it's low reagent use and buffer usage. Most of our kits actually run at using 500 microliters of buffer in each vials. And I actually mentioned that I was using 1 mil when I was running the test mix, but we could have run it perfectly well with 500 microliters. And the reason why I bring in the 500 microliter mark is because, of course, there's savings there. So you have twice as much. And our kits are actually tested to run at 500 microliters, which enables you to do more runs per kit. And last but not least, I had mentioned that a system has to be versatile. And what I mean by versatile is it has to be able to run all these 6 capillary electroseparation. And that's what I meant by that. And this is why it was important for me to list those. All right. Next piece of the puzzle that I had presented was, what's my net charge, or my pKa relationship to my pH, the pH of the buffer? If you remember, basically, I had presented this table there that I've created, which kind of gives you a general idea as to where things are situated. We were using a system, let's see, there we go. So we were using a system that has a test mix with 3 components: benzyl alcohol, which has a pKa of 14.36, and phenylentrenoic acid, which has a pKa of 5.28, and then benzoic acid, which has a pKa of 4.19. Now, in our system, we're using a borate buffer that is at pH 9.2. So therefore, if we take my chart, and you can trust me on this, we will have a negative charge for N-phenylentrenoic acid and then benzoic acid, and of course a neutral charge for our benzyl alcohol compound. And this is how they're going to show up in the electrophoregram. So another piece of the puzzle. And then one big piece of a puzzle that I had presented to you was the electroosmotic flow. If you remember, I played a little video with a baby that was walking on an airport walkway and was being pushed away from her mom. Basically, that's what EOF does, is it actually sweeps everything off of the capillary, and it'll sweep everything in this particular order. All positive charges will come out first, then the neutral charges, and after that, the negative charges. So keep that in mind. EOF occurs when we're at a pH around 4.0, but past 6.2 is where we start getting the most electroosmotic flow, which is called EOF. So, as you recall, this was the results that I was showing you guys. Benzyl alcohol's coming in first because it's a neutral charge molecule compound. We don't have any positive compounds, but they would certainly come out before benzyl alcohol. And then after that, we have N-phenylentrenoic acid and then benzoic acid coming out first. And of course, what we see here is the electrophoregram that I've shown you many, many times. But what we're going to move into now is, how do we obtain this data? And this is the next part of the puzzle that I want to include in how to set up a very good capillary zone electrophoresis method. And it is, of course, you probably already guessed, the software. And then the software plays a very important role, and it's something that we tend to forget, especially when I come across people that are making their homemade systems. Of course, if you buy any commercial system, it'll always come with a software. Our software is called LFORun, and there's several things that I like about that software. The first thing is that it's very easy to use, and I'll actually demonstrate that to you in a few minutes. You'll see how easy it is to use. In a couple of clicks, you've done so much work. Compared to other softwares that I've worked with, it's fairly simple to set this software up and start getting not only qualitative data, but quantitative data as well. So without more time here, what I'm going to do is I'm going to jump into the software demo video. The demo lasts 30 minutes. I'm going to stop the slide presentation here. We'll click on the video there, and I recommend you guys take close attention to this video on the software, and then make sure as well that you take any notes. Any questions that you have, write them down too, so that you can actually put them in the chat. Or if you want, you can type them directly in the chat. I'll actually be chatting along as we listen to the video, so that you guys, I'll clarify a few things from the presentation. Okay, so I'm going to start the video right now, and I will talk to you guys in 32 minutes exactly. See you later.
All right, guys, we're going to jump into the software portion of our training, of our demonstration here. The software that we're going to be running is called LFORun. And in order to launch LFORun, you just need to go ahead to double click on the desktop icon. I'm actually highlighting it right now. I'll double click on it, and what you'll see is a splash screen that's going to appear, showing you LFORun, and then we're jumping into a box, and it'll enable us to put in our operator name in there. So double clicking right now, double clicking again, sorry. There we go. Operator name, and then I'm going to type in my name in here, Patrick. I'll say OK, and this will launch the software. And the first thing that the software asks you is, do you want to turn the coolant pump on so that we can reach our temperature of 20 degrees Celsius? So just before I say yes to this, because of course we'll always be saying yes to this, we go right here and we check our temperature here. Right now it's reading 22.44, and our target temperature is going to be 20. So you'll see here in brackets the target temperature appear once I click on yes. Right there. So you see my temperature in brackets right there, 20 degrees Celsius. And this is the current temperature, so what this is reading. We need the temperature to be exactly at 20 degrees Celsius in order to be able to start our program. So the software works in a couple of modules within the software. We're going to be looking at the auto sampler module and the program module for this part of the software. So I'm going to go ahead and click on the auto sampler, and this pops this nice box here is the auto sampler. The auto sampler is the carousel basically, and it's showing us all the positions where we have vials, and those vials are the vials that we're going to be using within our program. So I've already enumerated this when I was loading the vials up. You'll see that so vial position number 1 is our 0.5 normal or molar, because it's the same thing, sodium hydroxide. Our vial number 2 in the inlet side is water. Then we've got the background electrolyte for rinsing, which is our rinse buffer. Background electrolyte for analysis, which is our separation buffer. And then in vial number 5 is our test solution. If I go further down, you will see that the color changes, and all of a sudden this inlet becomes the outlet. So starting at vial 36, as you remember, I told you from vial 1 to 35 is where the inlet vials are, and then from vials 36 to 59 is where the outlet vials are. And in vial 36, we've got the waste, which is where all the liquids will accumulate from the rinses. And vial 37 is our background electrolyte for analysis, which is our separation buffer on the outlet side. So this will make a bit more sense when I go through the program. So I'm going to scroll back up. I'm going to pull this window right here. And then we're going to go ahead and click on the program. This opens the program box. I'll reposition the program box just about here so that we can see everything that we want. And I'm going to load the program that I'm going to be using, which is our IQ program. It's right here. Now, programs can be saved anywhere on your computer. No worries about that. And you'll notice it's called iq.prg. So the PRG stands for the extension for program in our software. I'll click on open there, and boom, we've got our program opened up. And I'm going to go through each operations individually so that you guys have a good grasp of what is going on. You've noticed that I've got 4 rinses, 1, 2, 3, 4, an injection, and then an analysis step. And then I have an auto sampler and a standby mode operation right here. Here under parameters, we can type in some notes. I didn't do that. Right here, this column here is called cycle. And everywhere where there's a number here, it indicates that all of these operations are part of a cycle. I'll give you a quick explanation of what a cycle is. Right here, inlet and the outlet is pretty much straightforward. It indicates the inlet and the outlet position vials that will be used for this particular operation. So as you can see, first rinse is inlet vial number 2 and 36. 2 is water, 36 is our waste, as I've shown previously, and so on and so forth. So vial number 1, the second rinse will be sodium hydroxide. Vial number 2 again, we're going to be doing more water rinses in between the sodium hydroxide rinse. And the last rinse will be our rinse buffer, which is the separation buffer. And all of this goes into vial 36, which is our waste vial. Right here is the duration of the rinses. So though this duration here is in minutes, and so it's 2 minutes across the first 3 rinse, and then the last rinse lasts 3 minutes. I always like to put an extra minute for my buffer rinse to make sure that there's it's really filled with buffer before I go on and do an injection. The pressure right here that you see is 1000 millibars, and we're not applying any voltage. There's no wavelength here because we're not collecting any data at this point. Temperature is already set at the beginning of the method, so there's no temperature here. And then the status, I'll show you this later. It indicates what is the status of this particular operation when you start running a program. So when you start running a program, you click on the run right here button. If we go to the injection part, you'll notice that I've got 5, 5, 5, 5. This means that I'll be injecting 4 times from vial number 5 to vial number 37, which is our separation buffer. This time we'll be doing a separation for an injection for 5 seconds, not 5 minutes, 5 seconds at 30 millibars. And once this is done, we're going to jump into the analysis stage. So the separation voltage of 25 kilovolts right here will be applied across vials number 4 and 37, which are our separation vials, for 7 minutes. And we'll be monitoring everything at 205 nanometers. And this is going to go on repeating this cycle of 4 rinses, 1 injection, and the analysis 4 times. So everything that has a cycle with a number 1 there, this is going to be all repeated 4 times because I've got 4 injections. Once the cycle 4 is finished, then it'll move on to the auto sampler operation, where it's going to park the vials in the up position to the capillary cartridge, vial inlet 4 and 37, which are our separation vial buffers, which means it's going to put the vials up in buffer so that the capillary doesn't dry up. And then the standby mode actually turns the lamp off, so we're not using our lamp for unnecessarily. Let's go and dive in a little bit more into the operations. So I'm going to click on the little plus sign here. So what I've done so far is just kind of summarize the operation. But right in here you'll see, first of all, this first line there says cycle. I've actually checked it because this is part of the cycle. It's part of the cycle that it has to repeat 4 times in order for me to do my 4 injections. So this is why this is checked. Inlet vial 2, which is water right here. Outlet vial 36, which is, scroll down, our waste vial right here. So this is going to do the water rinse, as I've explained previously, for 2 minutes. And here's the time unit right here, 2 minutes, at 1000 millibars. So this is our water rinse. And you'll notice that because I highlight these, I'm actually able to edit the numbers here. And this is how I would edit the numbers on my method. Okay, now that we've seen the first rinse, let's check the second rinse. There's not a lot of difference from the first. The only thing we're doing right now is we're moving to vial number 1, which is sodium hydroxide. And vial number 36, what we've seen previously, is our waste. Again, for 2 minutes at 1000 millibars. And again, this is where I would edit everything out. The cycle, again, it's part of the cycle. I want this to be repeated in between my injections. And then I'll do the same thing. Again, I'm repeating the rinse for water for 2 minutes at 1000 millibars. Last rinse is our buffer. So it's our background electrolyte for rinsing right here. And then vial 36, which is our waste that you guys already know, for 3 minutes at 1000 millibars. Once all these rinses are done, then we're moving into the injection stage. So the injection, as I mentioned before, I've got 5, 5, 5, 5. So that's going to be what's going to be driving the cycle, meaning that I'm injecting from vial number 5. Once I've done the first cycle, I'm going to move on to repeating all these operations again, rinses all the way down to injection, and then do another injection, and so on and so forth until I reach the last vial in the cycle. Then the cycle is finished, and we move on to the operations that are outside of the cycle. So of course, cycle here is checked because it's part of the cycle and it's actually what's driving the cycle. Remember I told you earlier 5 seconds, here's the 5, and here's the time units are in seconds. And typically injections will go from 5 seconds to 10 seconds at 30 millibars. It's most likely the norm. If you'll notice, 30 millibars is about 0.5 psi. And a lot of papers, when you read them, yeah, it's around that, 5 to 10 seconds at 0.5 psi or 30 millibars. So once we do the first injection, we're going to move on to the analysis part, which is still part of the cycle because there's a number 1 here and the cycle is checked. So we're separating from vial number 4 to 37. It's going to take 7 minutes to complete this operation. And we have a 1-stage separation, which consists of applying 25 kilovolts and looking at the data coming out at 205 nanometers. Once all of these injections are done, as I mentioned previously, then we're going to move on to the non-cycle operations. So it's going to go to the auto sampler. As you can see here, quite simple. It goes to vial number 4 and 37 in the up position. The up position here is checked and falls into standby mode, which turns the lamp off. And that's it. So that's a very basic program here. Once you're ready to start, that means that your temperature has reached a set temperature. So as you can see right here, we've reached 20 degrees Celsius. Then we would click on run, which is what we're going to do right after this. And the program will start, and then you'll start seeing stuff populating in the status part of it. All right? Don't forget also to turn your lamp on for 30 minutes. And that's the first thing I do when I walk in the lab. I'm repeating it again. I'll actually turn the temperature on and then turn the lamp on. If your system was powered down, then when you power it up, it'll actually turn the lamp on automatically, but it doesn't turn the coolant pump on. That only happens once you launch the software. All right, so we'll move on to setting up a run. All right, guys, so we're going to jump into starting a run. Press run. It'll say the message that I've mentioned earlier when I was doing the hardware presentation. The door is open. As I mentioned previously, the door can stay open all the way until we reach the analysis portion of the program. And Normally I'll actually close it right before that, after I've viewed that my capillary is not blocked, the procedure I was showing you earlier, and that's the best way to do it. One other thing that I'm actually going to pop up the EPG signal window here, and I'll show you why I'm doing this in a few minutes. Just before we do that, I'd like you guys to pay close attention to the program. You'll notice that we're on the first rinse. So we're rinsing from vial 2 to vial 36. At the end, the status says it's being carried out. And then if you go in the middle part of the screen where it says operation, you'll notice that there's a rinse, and there's a little blue line there that's kind of filling up. Right underneath that, there's current time, so it's the time that we're running into. So we're closing into 92 seconds now. And once it reaches 120 seconds, which is 2 minutes, then we're going to move on to the next step. And so you'll see this happen. You'll see the status changing from carrying out to done. And then we'll start rinsing from the second vial, which will be from vial 1 to 36, which is sodium hydroxide, if you remember correctly. So we're actually moving into the next rinse right now. There again, it says carrying out. And now I want you guys to pay close attention to the EPG signal in the signal box. You will see in a few seconds this signal go up to about 220 milli-AUs. Why am I giving you this indication? This is another troubleshooting tool that we have, which is really cool. It tells us if our capillaries block here as well. Whenever you are rinsing with sodium hydroxide, expect the value to be about around 220 milli-AUs in the positive range, because it actually will have done an auto zero on the first rinse, which is water. And normally sodium hydroxide absorbs a bit more than water, so this is why you would see this jump to plus 220 milli-AUs. It tells you that your capillary is really good. It's working well. And so it's going to carry over and do the rinse all the way to 120 seconds. So as you can see, the status again says carrying out. The rinse part of the screen here where it says operation, you see the current time. We're closing in now again to 95 seconds, and then we're setting up to 120 seconds. So as it's moving further in, it will complete this rinse. And then what I've just told you, you'll see the next rinse is going to be water again. And then that EPG signal is going to fall into the negative range, because it's going to do an auto zero on the residual leftover sodium hydroxide rinse that we're doing right now. So there we go. We're moving to the next rinse, which is water. And in a few seconds, you'll actually see the jump into the negative number values. It's around 15 seconds. That's where it kind of jumps in. And it's going to go to minus 220 because it's water and it doesn't absorb as much as sodium hydroxide. So again, everything that I'm telling you here is to show you how the program runs, and then giving you some instructions on how to check to see if your capillary is blocked. So it's pretty cool. Remember, the sodium hydroxide rinse is used to regenerate your capillary walls for a bare fused silica capillary. Very important. If you're using a coated capillary, you should never use sodium hydroxide, because you're going to strip the coating off of that capillary and those are very expensive. And there we go. So we're going through the last step of this rinse. And once this is done, we're going to jump into the data processing. So I wanted to show you like a real life snapshot of what was going on while we were starting a run. All right, guys, so now we're going to jump into the data analysis part of the software. And here we go. So in order to do data analysis, we're going to need to open some EPGs, electrophoregram graphs. So these are the runs that we've collected for our IQ run. And as you remember, I'm going to open run number 2, 3, and 4 because these are the last runs that I want to do tests on. I'm going to go ahead and open those. I'm going to highlight them and click on open. And they're all going to open in the background right there. So I'm going to close this window up. And here we are. So we've got all of our electrophoregrams. And I'm going to use run number 4 to create another part of the puzzle, which is the method. So the method enables us to do quantitation. So builds the calibration curve, we're able to name our peaks, and we're also able to do statistics. So what I'm going to start doing is I'll start naming my peaks. So I'm going to highlight the first peak that's detected. And as you can see, it's highlighted in red. And this is benzyl alcohol, our first peak. And as I type in the name, when I click onto the next peak, you'll notice that the name appears on top of the peak. And then the second peak is highlighted in red, and that's our N-phenyl. Phenyl L-anthranealic acid. Hopefully I'm writing this. And there we go. So all peaks are now named. And from this run, I can actually create my method now. And I'll be able to apply what I've just done here on all of my runs by using the same method. So as you can see, all my 3 peaks are named here. I'm going to go and click on the method tab right there. And then what I'm going to do is I'm going to click use for calibration. This is how you create your method. And then I'll click on create method. And then I'm going to call this method IQ method. And then I'll click OK here to save it. And now I've actually changed it to the IQ method. That means that this is now, for this run, this is the method that's going to use to do quantitation. And then I can go ahead and click on this little diskette here that says Save EPG. Or if I accidentally close the window, it'll tell me, hey, you want to change, you want to save the changes. So I will say yes. And boom, my run is now saved. So as you can see, I'll repeat this with run number 3, but it's a little bit different here. What you do is you just go to the method tab and you just click on open method, pick the method that we've just created, which is the IQ method. Click on open, check and make sure that all the peaks are labeled properly. And then I can click on save EPG. And that's it. So now this second run is saved with the information, and I'll repeat the same for run number 3. Boom, Open method, IQ method, okay. All the peaks are named, perfect. Save EPG, bang, and that's it. So now I've actually loaded up my data with the method that I've created. And this will enable me to do some statistics. So how do we do statistics? Again, if we go back and open our EPGs, I can highlight all the EPGs now that I want to open. And then under open, I can say open in set. And what's that's going to do is it's actually going to open a window. It'll stack all the runs onto that window. So right here. And voila. Everything is there. So if I highlight number 2, this is number 2, this is number 3, this is number 4. So I can go ahead and maximize this big peak here, which has been benzyl alcohol. You'll notice that this peak has a very funny shape, and it's because it's neutral. So it's moving with the EOF. Let's back up a bit and now highlight the N-phenyletranilic acid. You'll notice that that one is actually a more pointy peak. And these are the stacked runs. So as you can see, the migration times are pretty good on these. And then same thing for our benzoic acid. Migration time is pretty straightforward. But if we want to have absolute numbers to it, we go ahead and click on the statistic tab right there. And then I need to highlight everything that I want to compare statistically. And I click on apply here, and bam, I get the actual numbers. Because some people might say, yeah, they don't look that much the same, but they really are. We're talking seconds in difference here. So as you can see, normally what I like to pay attention to is our time, migration time. So migration time for the neutral marker is 0.4 RSD and 0.7 on the peak height, which is really good. And then if we look at the actual peaks that we're interested in, that's the ones that we actually check when we do the IQ. I've got a 0.5% migration time for the N-phenyletranilic acid and a 1.7% area, peak area, actually, actually 0.1% peak area. Sorry, that's peak height, the second peak. So 0.1% peak area, so we're pretty much bang on. And benzoic acid, 0.5% RSD migration time here as well, and 0.1% peak area. So really good data here. And of course, I'll typically be, when I do an IQ, I actually compare this to a set of standard runs, and they have to be below 10%. When I see data like this, I know we're right on board here. So our capillary is performing really well, and so is our system. And that's pretty much the third part of the software demo, the last part as well. So if you have any questions or anything you need to know, please don't hesitate to contact us. And that'll be it for the full demo. So hopefully you liked everything and you learned a lot as well. And as I said, don't hesitate to contact us for additional information. So thank you so much for your time. Thanks for, going through this whole demo and listening to me. Greatly appreciated. Take care. Talk to you soon.
All right, guys, so we're back. Thanks for listening to the video. There were a couple of questions that kind of popped up in the chat. as we were viewing the video, and one question was in terms of the number of rinses. So what must be the minimum number of rinse? And if the question is geared in, say, time, the capillary I'm using right now on this demo is a 60 centimeter total length capillary. And there are tools actually on the web that are out there that tell you how much volume you need to have one full volume to your capillary. But typically here, I would say for 60 centimeters, I would not go below 2 minutes. There'll be people that'll tell you, well, 1 minute is more than enough because it's greater. It does actually exceed 10, what we call 10 capillary volumes, 10 column volumes. If you guys are familiar with HPLC, we need to have at least 10 column volumes before we go on to the next injection. So in terms of time, I would say it would be safe to keep the 2 minute range as a minimum target. Now, if the question was geared towards, well, how many times do I need to rinse in between runs? There's several discussions on that by many people, and typically it's a trial and error thing when you're testing this out. What I would say is that you would need to check and see when your migration time starts to slip away. So kind of like if I go back in my slides here, that actually will be a better way to show you what I mean by that. If I go back to the results here. So as you remember, I was stacking all the runs together, and what I was seeing is an RSD that was very low, 0.5% RSD on migration time. Well, what would happen is eventually, if you don't regenerate those capillary walls and you don't rinse properly, these peaks are going to start to move further away in the electrophoregram, so therefore they won't come out at the expected migration times. And that's when you know, well, you need to rinse. And that's in terms of regeneration of the capillary walls. But in terms of rinsing buffer through your capillary, that has to be done every single injection because you need fresh buffer for every run. Hopefully that answers that question that I had on the chat. And guys, if you have more questions, feel free to pop in on the chat there and put them in there. And I'll be more than happy to answer your questions. You're welcome, Sina. All right, so now the results part, I'm jumping into this from the video that we've just watched, and basically what I'm showing you here is now you have a better understanding of how things have been set up for integration. We only scratched really the surface on what LFORun can do here, but I don't know about you, but to me, with my experience, this is probably the most simple software that I've dealt with to set up for quantitation. It's like a couple of clicks and you're there. So basically, this is, I was mentioning this on the chat, this is a really great feature of this software LFORun. You can also install LFORun on more than one computer. There's no licensing that's attached to it. So sometimes it's so fun to have like a version of the software that you can take home with you so that when you're a student, you can work on your data offline. So that's another great feature that I really love about the software. And of course, the statistical analyses as well, which I'm going to jump into right here. Let's click right there. This right here, this is becoming more and more important for people that are writing papers, because a lot of people are being asked, well, how reproducible is this? Well, here you go. And one quick way you can actually show this report to say, well, here, this is how reproducible this is. So that's really great. It's a great tool to have for anyone that's writing a paper, or even for people that are experiencing any quality control type environment. This is definitely the tool to have on hand. All right. So I don't see many questions here. That's fine. You guys still can write stuff once we're done with the presentation, but I'm already at the point where my last part of the presentation, which if you need more information, and I put up this slide because you guys have seen this on part 1 for the ones of you that were there. We're all over the place. We're really all over the globe. And basically we have worldwide support. And we've listed the main offices here on the map here. And also where you see everything in blue is where we have instruments. And of course, if you see a spot where you live, there's no instruments there, well, we'd like to correct that. So feel free to reach out to us. I've actually typed in the info@lumexinstruments.com email. And when you do reach out to us, please mention from which region you are in the globe so that we can actually get someone that is supporting your region to answer you back in terms of that. And that's kind of like how there's many experts in several fields across Lumex Instruments. And even sometimes we actually chat amongst each other to get the best answer to our customers. So no worries. I'm pretty sure anyone you'll interact with will give you the right answer. All right, let's go back into those slides here. And I wanted to end on this note here, and I've shown this on part 1, but it's such an important message here because a lot of people, again, this is nothing that I'm inventing here. A lot of people come to me and they say, well, why should we use capillary electrophoresis? And I tell you right now, I mean, you can see I'm very enthusiastic about CE. I've been working with CE for like 23 years, believe it or not. And I had a little bit more hair at the time. Anyways, in regards to that, this is why you should be using capillary electrophoresis for certain of your applications. What we're looking at right now is an HPLC run of a peptide mixture composed of 5 components, so 5 peptides that are being separated close to 60 minutes actually here, the separation time. It's a TFA 0.06 with acetonitrile gradient that's being used there. Why do I know this? I've actually worked 7 years in research doing these type of separations with an HPLC. And when CE first came up in our lab, we actually were playing around, testing several things, and we kind of had fun with it at the time. And it's still a very awesome tool to have because there's a couple of things that do occur. But this HPLC run is fine if you look at it by the standpoint of, hey, I've got baseline separation. My peaks are very well resolved. I can quantitate with this. So why would I move into a capillary electrophoresis type system? Well, here's why. This is the same peptide mixture, but now it's been ran in capillary electrophoresis system, the Capel-205 actually. And I was tasked by a customer. They asked me, hey, can you run any proteins or peptides? And of course, we went with the peptide mixture here that was commercially available from Sigma Aldrich. And as you can see here, I've got my 5 peaks. They're very well separated. You can actually quantitate here, no problems. And one thing that you probably haven't noticed, or maybe you have, everything comes out before 16 minutes, which is great. That means you can do like 4 runs for the equivalent of 1 HPLC run. So you're saving a lot of time, a lot of money, because TFA and acetonitrile are not cheap. Here, what I was using was a PBS background electrolyte. I'm not going to say buffer because it wasn't buffered at that pH, but it's a PBS background electrolyte at pH 3.0. And pH 3.0 using a bare fused silica capillary, there's no electroosmotic flow here, so we're only dependent on the charge of the actual compounds that we're trying to separate here. And of course, here we would talk about the pKa of those peptides. And that's kind of how I was able to use everything that I've taught you on part 1 and today to get this separation to occur. Of course, I did do a little bit of trial and error on certain buffers as well, and this buffer proven to be the best one. And this is the cool thing about the Capel-205 is you could set several buffer systems inside the instrument and let it run overnight, and you'll get an answer pretty quickly. So sometimes methods development can take a lot of time. With CE, mostly I'd say within a week, you'll have a lot of data that will really guide you as to where you need to go. So again, this is one of the reasons why is to use CE is that it uses so less reagent, 500 microliters, remember that I mentioned previously, and there's not a lot of waste that's being generated for that, so it's good for the environment. And then of course, you're running it 4 times quicker here for this particular example. So that's all good positive stuff that you can bring back to your boss, or even, you know, convince yourself about using capillary electrophoresis. I'd like to end with this particular slide. Again, this is something that I actually was showing on part 1, which are the things that I need to know to set up a good capillary zone electrophoresis method. And of course, it's rehashing all the step-by-step points that I was telling you guys earlier. So the pKa or the pI of my compound of interest, what's the pH of my buffer or my background electrolyte? Do I have electroosmotic flow? Remember, above pH 4 and even past pH 6.2, this is where EOF starts to go high. So you have to be aware of that. Which polarity should I use? Of course, it's the orientation of your electrodes. If you don't have any EOF, or if you do have EOF, it's important to know where the positive or the negative electrodes are. And what you want is you want to set them up in a way that everything is migrating towards your detection window. The buffer concentration, we didn't mention a lot of things about the buffer concentration. And one rule that you'll see is the higher the buffer concentration, the better the resolution and the stacking of your peaks become. But there is a trade-off here. And as you know, in chemistry, everything has to tend to equilibrium. So here, if we have too much of a high concentration in buffer, well, we're going to have what we call a current leak. The system's going to crash and there will be no separation. So you'll see there are some papers that exist out there that actually have tested the buffer concentration, and people have found the buffer concentration that actually is the best for the better separation and making sure nothing crashes. Of course, in order to go to the higher buffer concentrations, you need to be able to control what we call the Joule effect, and that's the temperature of the capillary. So we really need to control that very, very, very heavily. Again, as I mentioned, there's a cooling pump with water and a little bit of methanol in it, 4 to 6% methanol, that keeps everything cooled so that you can go to those higher buffer concentrations and those higher voltage settings as well. And then the last piece of the puzzle that I've added today was we need to have a software that's really easy to use. And I think I've proven my point here by saying that LFORun is a pretty simple piece of software to work with. So that's it for me. Thank you so much, man. There's like still pretty much everyone's still here. I'm so glad to see that. So again, thank you so much for your time, and I really enjoyed showing you CE. And of course, if you guys have any questions or anything, the webinar will remain open for another 15 minutes. I'm gonna go offline, but I will be looking at your questions if you have any, okay? Thanks a lot for your time again. Have a great day, and happy holidays. Bye-bye.